Hello everyone, welcome again. So today's lesson will be on the metals module of Year 11 Chemistry. And in the previous two lessons we've talked about what a mineral is and what an ore is. And now we're going to sort of take our journey a little bit further and look at how those minerals and ores get turned from their mineral form into the pure metal form that we use in industry. And in order to do that, we're going to look at how copper is extracted from its ore form all the way to when it's pure copper like this. Okay, so we're gonna study the extraction process by looking at a case study of copper. Okay, so copper, firstly we need to understand what copper is used for so that we can understand why we need it. So copper is used widely in industry, and its major use is in electrical devices as it has an excellent level of electrical conductivity. So copper wire is very common because it's just a very good electrical conductor. Okay, so how do we refine ores? Well, in nearly all refinement processes, there are 4 steps. There's mining or extraction. So this is where we find the deposit, we dig it out of the ground, and we put it somewhere else. Okay. Then milling or concentration. So once we've got the ore, we crush it and remove some of the waste rock, and then we get a slightly more concentrated amount of metal, and so that's what we want. Then there's smelting. So smelting is sort of when we get we take out even more of those impurities and get an even higher concentration of metal. And then finally, if we need it, there's the refinement process where we can get ultra high purity metal, either through the use of electrolysis or some other chemical process, to get to almost 100% purity in terms of metals. Okay. Okay, so copper mining. So around the world, copper is a pretty significant industry. Australia is a big exporter of copper, and many other countries around the world also dig out copper from their soil and sell it to other people. Essentially what happens is when we dig out copper ore, we dig it out of the ground in these large open cut mines. So here's an example. This may not look very big, but the scale of this is probably enormous. But it's essentially all an open cut mine is just a giant hole in the ground. So it's not very deep, so it doesn't go very deep into the earth, but you can see the area that it takes up is very, very large. Okay, so while it's not very deep, it's very, very large in terms of its area. So it means that a lot of rock has to be moved, and it's not the most attractive site, but it's how we've learned to mine things out of the ground in these large open cut mines. Now, what's surprising is that when you actually are looking for a economic deposit of copper, the copper percentage in the ore could be as low as 0.15%. Okay? So what does that mean? Well, that means that it's oops. Hang on. Nope, that's not right. So it's 0.15%, which is 0.0015. Yep. So as a fraction, this is how much copper you have. So in 1 ton of the rock that we dig out here, 1 ton, we can get 1.5 kilograms of copper. Okay, so we dig out 1 ton of rock and all we get out is 1.5 kilograms. Okay, so this is a tiny percentage. But the only reason why we can do this is because the copper is in quite big deposits. The deposits are quite large, and our mining and extraction processes are quite advanced. Okay, so once we've dug it out of the ground in our big hole, we need to do the next process, which is milling. So it's also called concentration because we're taking that 0.15% copper and we're concentrating it by getting rid of some of the waste rock and sort of getting a more concentrated amount of copper. Okay. So essentially this milling process removes the waste rock, which sometimes is called gangue, from the ore. So what happens is we take the ore, we crush it in like a rock crushing device and make it into a fine powder almost. And then we mix it with water in a tank. So once we get this powder, we mix it with water and we mix it in a tank. And then we add a chemical and then we stir it some more. Okay, so we add a particular chemical and then we stir the rock water chemical solution. Now the mineral, the chemical that we put in essentially causes the copper compounds, anything with copper in it, to stick to the bubbles created by the mixing process. And so what happens is you get a tank that is stirred with bubbles because it's stirred with air, and the copper will kind of stick to the outside of it, of these bubbles. Okay, and where do bubbles go? Well, they go upwards. So what happens then? So the rising copper compounds in the bubble, connected to the bubbles, form a froth, which then can be sort of skimmed off the top. Okay, so it's sort of like skimmed milk or skim milk. So all the fat compounds sort of sit on the top. So we skim the fat off, and then what's left is the skim milk. Okay, it's the less fatty section. So you can see here in this picture, there's this weird sort of bubbly, silvery metal stuff that looks kind of out of a Terminator movie. That's the copper compounds in the bubbles. Okay, so they come to the top and formed a froth here. Sort of looks like one of the Terminators. And then what you do is you just skim that off, and then you've got suddenly more copper because you've gotten rid of that waste rock. So that's what we're doing. We're just skimming the top to get more copper. And it's a very good process because we've turned our 0.15% copper into 25% copper. So we've almost, we've made a big jump in concentration. Now it's about a quarter of this stuff, this bubbly stuff, is actually copper, which is good. We're getting there towards 99.9% copper. Okay. So once we have our little froth flotation copper, we need to smelt it. We need to make it even higher concentration. Okay. We need to get it up to a much higher concentration. So once we do the concentration step, most of the copper is in the form of some kind of copper sulfide, CuS. Okay? So the copper that we skim off the top is mostly in the form of CuS. And so we roast the copper sulfide, in oxygen, and the sulfur gets removed as SO2 and SO3. So sulfur dioxide and sulfur trioxide. Okay? And this reaction is similar to combustion and is very strongly exothermic. So it emits a lot of heat and light and energy. Okay, so the roasting process, you heat it up, you start it going, and then it releases a lot of energy, and it's almost self-sustaining process. So this process converts the copper sulfide to copper oxides. Okay, so it converts most of the copper sulfide to copper oxide. Okay, then the new mixture is exposed to heat again, and silica. And coke as well. So the silica is just there to sort of help the process, but the coke is the carbon, and so it absorbs the oxygen in the copper oxides and turns into carbon dioxide, and then you get pure copper out as well. So this reaction occurs at 1200 degrees Celsius, which is higher than the melting point of copper, producing a liquid called copper matte. Okay? So this process occurs at 1200 degrees Celsius, which produces a liquid copper called copper matte. And then this copper matte is exposed to oxygen once more to remove any remaining sulfur impurities. So what we've done is we've taken the copper sulfide, exposed it to oxygen, and got copper oxides, exposed it to carbon, which we get pure copper, And there'll still be some sulfide impurities in there, so we expose it once more to oxygen, and we get rid of that last bit of sulfide, and so we finally get to almost pure copper. And the product, the final thing, is called blister copper, which you can see here. And why do we call it blister copper? Well, if you look at it, it looks like this surface has become blistered. If you've ever gotten a blister, you'll know what I'm talking about. And basically, it's because the sulfur dioxide and carbon dioxide and all these gases has actually sort of warped the shape, sort of formed bubbles inside the copper, and has warped the shape of the copper, giving it this blistered appearance. Okay. And at this point, the copper is about 98% pure. So that's really good. We've gone from 0.15%. Then in the concentration step, we went to 25%. Now in our smelting process, we've gone from 25% all the way up to 98%. Okay, so we're almost at 100% purity, which is really excellent. Okay, and then finally, we refine it. So if we want even purer than 98%, we can get there. So the blister copper is cast as an anode and placed in an acidified copper solution. So all that means is, okay, so you got a power supply here, and your blister copper sits there, okay, as the anode. And then you got a plate of pure copper on this side, and then you got CuSO4, copper sulfate solution, as the liquid. And so the electricity forces the copper in here to accumulate over here. Okay, and the copper that accumulates here is very, very pure. Okay, and then the waste just goes away. It just falls to the bottom. Okay, so this is what we call an electrolytic cell, and you'll learn more about this in year 12, but we're just going to brush over it quickly now. So don't worry too much if you don't understand it, but we will cover it again. So out of this process, high grade, 99.99% purity, copper can be used as the cathode. So we have to get very, very, very pure copper at the other side. So you know how we had the copper on this side. It needs to be almost 100% pure. So then when electricity is passed through the cell, so when electricity has gone through that cell that I created, the copper in the anode, so the copper in the blister copper, sort of migrates towards the cathode, the other side. So we'll just draw it again quickly. Okay, so the copper from the blister copper here starts to migrate over to this way when electricity is applied. Okay, so it tends to migrate this way. Okay, and then it forms pure copper on this side. Okay. So the remaining components of the anode are referred to as the anode sludge. So once the copper has left this side, the waste kind of just falls to the bottom and forms a sludge, and we call that the anode sludge. Now the interesting thing about the anode sludge is that it contains noble metals such as gold, silver, palladium, and platinum. So it contains some very nice metals. So the copper sludge can actually be refined again so that we can actually get back these metals and make a little bit more cash if we're a copper refinement group. So that's very nice additional benefit of copper mining and copper refining. Okay. So that concludes today's lesson on copper extraction. We looked at a lot of processes, but the main thing is to remember the big four: mining, milling, smelting, and refining. So those are the four processes that you need to focus on, and that's all we've covered. Okay, but there are a lot of intermediate processes intermediate steps in each process. So I do understand that it's a very long process. So just try and remember it, and you can always watch this video again if you've forgotten something. But we'll move on to the question segment now, and I'll try and pick out the best parts of best information for you to remember for your exams and things. Okay. So in the first copper smelting step, CuS is reacted with O2 to form Cu and SO2. Write a balanced equation for this step. Okay? So we start with CuS and O2, we form Cu and SO2, and if you look at it, it's balanced already. So very, very easy one to write. Okay? So very little additional fuel is required to maintain this reaction. Explain why this is so. So how come we don't need to keep heating up, keep fueling this process? Well, this reaction is very similar to combustion reactions. And these reactions are extremely exothermic. So the high heat release means that the temperature of the reactor can be kept high with very little input of energy. So because each of these reactions is emitting heat, it can actually help keep the temperature up at a very high level without having to keep putting in more fuel because the energy is coming from this reaction anyway. Okay. Question 7. The first process after mining is milling. Explain why the copper ore is crushed into a fine powder before any of the reaction steps. Okay, so before we start using any chemicals, we crush it into a very fine powder. Why do we do this? Well, crushing serves two purposes. Firstly, it helps separate the useful metal from the gangue in a mechanical way. So we can take the metal and we can extract it. We can take the useful part of the rock and filter away the waste rock using a mechanical process. And secondly, obviously, I think you've realized this now, but the biology students would definitely have seen this already, that the greater surface area created by the crushing process allows for a faster reaction rate in the future chemical processes. So if we actually crush it, we can have the reactions happening faster, which is of course good for business because we can get more of the copper out because the reactions are happening faster. Okay. Question 8. Explain why electrolysis is not used in the first step despite achieving the greatest purity of copper. So, we've got this copper ore, it's 0.15% copper. So why don't we just use electrolysis and see if we can just take out that 0.15% and have 99.85% waste. Well, electrolysis is a very energy intensive process. By concentrating the copper in the previous steps, reduced energy requirements can be achieved. So by concentrating it, I can actually reduce the amount of energy I need to use during the electrolysis step. Additionally, since there's less waste, because we're concentrating the copper, electrolytic cells do not need to be cleaned out as regularly, resulting in reduced maintenance costs. Okay? So because there's less waste, I don't have to clean out the waste all the time, and so I don't have to maintain it as much. I don't need people to clean it out. I can just have it there working all the time. This was all under the assumption that the copper ore was electrically conductive in the first place. And if it wasn't, well, then we couldn't use electrolysis on the non-conductive ore because electrolysis is about electricity. So it needs to be at least suitably conductive for electrolysis to happen. So all of this answer was predicated on us assuming that the copper ore was electrically conductive. But if it's not, that's just one more reason why we can't do it. Okay? Okay, so question 9. An economic deposit of copper can have copper percentages of 0.15%. Explain advances in chemical processes and mining techniques which have made this possible. While advanced mining techniques have allowed for greater and more efficient mining operations. This allows more rock to be moved in the same amount of time. So, because our mining processes have gotten better, we can actually extract more rock in a given time than we could before. Advances in chemical processes has allowed increasingly copper scarce rock to be concentrated into purities high enough for electrolytic refinement. So before we had to have copper with a high percentage, copper ore with a high percentage of copper. But now, because our chemical processes have gotten so good, we can actually use very little copper percentage rock and concentrate it into purities that are very high so that we can use electrolytic refinement. together, these two advances have led to a greater ability to tap low-quality ores. Okay, so the low-quality ores that we couldn't mine before are now possible because we have such high-level mining and chemical techniques to refine and extract these copper metals from their ore. Okay. Okay, so copper ore contains chalcopyrite. If the reaction only involves O2 and produces Cu, FeO, and SO2, write the balanced chemical equation. Okay, so we've got this chalcopyrite, and we know it involves oxygen, Cu, FeO, and SO2. So what's the chemical equation? Well, for starters, I like to write the quasi-balanced chemical equation. So what that means is just I write the products and reactants. Okay, so I know this goes in, and I know this goes in, and I'm told that this and this and this come out. So I'm just going to write everything down, and then I'm going to balance it. There's no point trying to balance this in your head. You might as well just write it down and then work through it. Okay, so I'm going to balance the sulfur first. So there's 2 sulfurs on this side, and there's 2 sulfurs on this side. So now it's balanced. Then I can balance for oxygen. Now the reason I didn't balance for iron is because there's 1 iron here and 1 iron here. And I didn't balance for copper either because there's 1 copper here and 1 copper here. So it was already balanced, so I don't need to worry about that. But all I have to do now is balance for oxygen. So there's 1, and then 2 times 2 is 4. So it's 5 oxygens on this side. There's 2 oxygens on this side, so we're in a bit of a pickle. In order to get 5 on this side, we need to multiply by 5 on 2, which is okay, that's fine. So I multiply by 5 on 2. Now if you don't like that fractional coefficient, you can get rid of it just by multiplying everything in the equation by 2. Okay? So don't worry about that. If you want to get rid of it, just multiply the whole equation by 2. But you don't have to. This is okay. Okay, and there's your final equation. Okay? So that concludes today's lesson on copper extraction. We looked at the whole process of copper extraction, and it was quite a lengthy one. So please view this video again if you had trouble following everything. And so we looked at the 4 major processes: mining, milling, smelting, and refining. And then we did some questions based on how these have affected copper mining, and also why we do some of these processes and the chemistry behind them. So in the next lesson, we're going to look at aluminium refinement. So I look forward to seeing you at our next lesson.